Part of optimizing Vulkan renderers on the host means reducing the amount of work you perform when recording command buffers. This is done by binding resources like a pipeline or descriptor set once for multiple draw calls that share them. Rendering for multiple threads, and especially setting up your data in a cache coherent format, can also have a massive effect on your performance, but that isn't our focus here. In this project, I'm loading GLTF assets into a scene struct that holds two vectors of draw objects which contain the necessary information to generate a single draw call. These draw objects are loosely correlated to what's called a primitive in GLTF, which contains a chunk of geometry to be drawn. They will also contain a pointer to a pipeline info struct, which bundles a VK pipeline and pipeline layout together. In our example, we're using three descriptor sets. One for global data, like the current view projection matrix, one for material data that contains image samplers for the textures, and one for per object data like a local transform matrix. In my VK backend class, I have a render geometry function, which creates a color and depth attachment, sets up the rendering info for dynamic rendering, and updates the first global descriptor set, which simply updates the scene to rotate in our case. We also have a lambda function called renderObj, which takes a single draw object for rendering. In its current state, it will bind a pipeline, set the view and scissor, bind all three descriptor sets, then issue an index draw call. Below it, we have two loops which simply iterate over the opaque and transparent draw objects and call our lambda for each. For our first optimization, we take advantage of the fact that pipelines can be bound once for multiple draw calls. In our case, we have a list of opaque and transparent objects that point to either an opaque or transparent pipeline info structure respectively. We can create a temporary variable to track if the pointer's address has changed. If it has, we know that we're now looping through the next group of draw objects and need to rebind a pipeline. This cuts our bind pipeline calls from however many draw objects there are to only 2. Next, we know that in the GLTF format, materials can be shared among separate primitives, and in our case, draw objects. This means we can do a similar technique for our material descriptor set as we did for our pipeline. For this to really work though, we need to sort our objects in a way that those with the same materials are grouped together. This helps to maximize how many objects can use the same bound material set. Currently, we're binding the global descriptor set for each draw call, which should really only be done once during command buffer recording. We could add another temporary variable for this with yet another if statement, but all these conditional checks introduces the possibility of a control hazard. This is where the branch predictor may predict incorrectly and some work the CPU went ahead and did ahead of time needs to be thrown away. In our case, this isn't a huge concern since this function will execute in the same way every time because we're rendering the same draw objects in the same order. Still, I think a better way to structure this is to move a lot of our command recording out of this lambda. First, we bind our opaque pipeline considering we loop through opaque objects first. Then we set our viewport and scissor once as this will apply to the entire command buffer, and afterwards we bind the global descriptor set once for all objects. Once all of our opaque objects are drawn, we update the current pipeline to the transparent one and bind it. This eliminates our conditional pipeline check, allows our global descriptor to be bound once, and cuts down our unnecessary viewport and scissor function calls. I set up a simple benchmark that times the difference between entering and exiting the render geometry function in microseconds. I accumulate these times into a variable each frame and divide by our total frame count during cleanup to get an average time. I'm rendering a car with 75 primitives and 14 materials with a really simple shader to add a bit of directional lighting. Running the renderer for a minute straight 3 separate times yields an average time of 14 microseconds for our initial version of our function. Running the same 3 tests on our finished version yields an 8 microsecond average on my CPU. This benchmark was very simple and our scene was not very large, but the overhead of doing unnecessary command recording scales linearly when dispatching hundreds or even thousands of draw calls. Renderers are very demanding and these optimizations do matter when you consider that modern CPUs can fit thousands of clock cycles into a single microsecond. Considering our improvement took a few minutes to implement, I think it's worth the effort. Thanks.